evening, I'm Chung-Ang P. This is CAU World Service and welcome to the engineers. You may think of the ground as solid and unmoving, but what if you told you that in structural engineering, the ground is sometimes modeled as a series of springs? That's right, it's called the Winkler foundation model, and it plays a crucial role in how we analyze structural behavior on soil. Let's go live to our field correspondent who's on our site with a closer look.
Thank you. I'm here to explain the basic concept of Winkler foundation model. Unlike real soil, which behaves continuously, the Winkler model simplifies the ground into a series of independent linear springs. Each spring reacts only to the displacement directly above. In mathematical terms, the soil pressure Qx is proportional to the beam's vertical deflection Yx using the formula. This simplification allows us to analyze complex structural behavior using numerical methods like the finite difference method. Now let's break down the main equation that governs this model. A beam resting on a Winkler foundation experiences two main forces: the internal bending resistance of the beam and the upward spring reaction from the ground. The balance between these forces leads to the following. This force order equation helps us compute the deflection of the beam, which we use to draw shear force and bending moment across the structure. There are two major ways to solve this equation. The first is the exact solution, which gives accurate results but is only valid for very simple cases. The second is the finite difference method. It's a numerical technique that divides the beam into small nodes and computes values step by step. In our project, we use the FDM since it's more flexible and easier to implement this method, especially for multiple nodes. Now let's go back to the studio, where our anchor is joined by a special guest. 황윤재입니다.
Thanks for that detailed explanation. We're now joined by our engineering analyst who developed the FDM-based MATLAB model. Could you walk us through how the code works?
Of course. First, the user inputs the number of spring segments and the position of the point loads. We construct a system matrix with n+1 nodes and solve it to get the vertical deflection. Then, we use second and third order derivative approximation to calculate bending moment and shear force using matrices and D. Finally, we visualize the result in both table and graphs. Here's the result table showing deflection, shear, and moment value for each segment. For instance, the maximum deflection is around 0.025 feet near the center of the beam. Shear force and moment value vary across the beam, reflecting the location and magnitude of the point load. We also plotted this result for clear understanding. The deflection curve is smooth and symmetric, and the shear graph shows sharp drop at the low point. The moment diagram has a characteristic curve where shear changes rapidly. This confirms that the finite difference method accurately simulates structural behavior when enough segments are used.
I've heard there's an extra feature in your model. Can you explain that?
Yes, for the extra credit, we added a feature where the user can input any number of loads. In the example shown here, we applied 3-point load, 250 kilopond at 6.5 inches, 200 kilopond at 121 inches, 210 kilopond at 198.5 inches. The system automatically recalculates the FDM matrix, and the results show how the deflection becomes negative beyond 30 feet due to the third load. The shear peaks around 1,537.7 kilopounds at the moment drops sharply after 30.3 feet. This flexible input system allows for more realistic simulation of structural loading conditions.
Thanks for the explanation. This is end of our today's news, and thank you for listening.